matrix space, we start from the definition of a contact point today. We have a matrix space X with the matrix D. And we have a subset A of the matrix space. Okay. This is the whole matrix space X with its matrix D. And we have some subset A of the whole matrix space. And we say that a point X naught on the matrix space X is a contact point of the subset A. That's what we want to define here. Okay? We have the whole matrix space X and we have a subset capital A of it on it. And then we say that a point X naught on the matrix space X is a contact point of the subset A. Contact point of the subset A if every neighborhood around X naught, every open ball around X naught, every open ball around X naught contains some element in the subset A. If for all positive number R, depending on that, there is some element X in the subset A such that the point X is in that open ball around X naught with radius R. That's the formal definition of a contact point, which is very close to what? The accumulation point on the real number line we have studied in the real analysis. Okay? So no matter what neighborhood, for all, I said for all positive number R, for all positive R neighborhood around X naught, no matter what R open neighborhood around X naught we choose, that open neighborhood must contain some element X in the subset A. That's what that means. Then if this has happened, then we say that the point X naught is a contact point, the contact point of the subset A, which is very close to the definition of the accumulation point we have studied in the real analysis last year. But honestly, I don't know how this open ball looks like. It totally depends on how the matrix D on it is defined, right? Even on the two-dimensional Euclidean space, on the two-dimensional R2 matrix space, depending on how the matrix D is defined on that R2 Euclidean plane, the open ball may look different. Of course, in our usual metric, we have used a lot. Okay, that open ball around X naught is exactly what? The disk around, right? But for some other metric D, which I don't remember precisely right now, but for some other metric D, the open ball around X naught looks like this kind of rectangular shape, something like this. That maybe happened, okay, for some other metric D defined on the Euclidean, two-dimensional Euclidean space, right? So honestly, I don't know. In general, I don't know how the open ball, this open ball around the X naught looks like in the general metric space. But that we still use this one, the disk picture over here for easy explanation. Yeah. So we say that a point X naught in the metric space X is a contact point of the subset A. This is the subset A of the whole metric space X, and then we say that the point X naught in the metric space is a contact point of the subset A if no matter what open ball around X naught we choose, we may choose larger or smaller open ball. No matter what open ball around X naught we choose, that open ball must contain some element X in the subset A. And we say that point X naught is a contact point of the subset A. Okay? Then, what is our next step? Our next step is to define what? The convergence of a sequence in the metric space. And then there is a nice relation between the contact point and what? The convergent sequence in the metric space, as you have already experienced in the real analysis last year, right? That's the next definition then, okay? That's the next definition. Let's let X of n be a sequence in the metric space. And let's let X be a point on the metric space X. Then we say that the sequence X of n converges to another element X. If epsilon n technique we have used in the real analysis. Okay? No matter what positive number R we choose, we use R notation instead of epsilon notation in this metric space theory. I don't know the reason why, but the people rarely use epsilon notation if we are out of the real number line. I don't know why, but that's, I believe, the conventional in mathematics. So, for every positive number R, depending on that, there is a cutting line. I still use the term cutting line I have used in real analysis. There is some cutting line n of R, which is a natural number, such that if the index n is more than that cutting line n of R, then the corresponding terms of the sequence is sitting inside the R neighborhood around X. That's the formal definition of what? The convergence of the sequence X of n to X in the general metric space. That's exactly the same as the convergence of the real sequence to a real number. Okay, we have studied in the real analysis last time. No matter what R neighborhood around X we choose, depending on that, there is some cutting line n of R, such that if we choose any index number which is more than that cutting line, and then what? The corresponding terms of the sequence must be sitting inside the R neighborhood around X. That's what it is about. Right? Here is the whole metric space X with the metric D, and then here is a point X, and then we have a sequence X of n's, right? X of n's. And then we say that sequence X of n is converging to that point X here if no matter what R neighborhood around X we choose. Okay? Depending on that, there is some cutting line, n of R. I don't know where it is exactly. Maybe here around, n of R, cutting line. Okay? Such that if our index n is more than that cutting line, then what? The corresponding elements are sitting what? Inside that R neighborhood around X. That's the rough picture of it. That's a two-dimensional picture. But actually, again, I honestly don't know how that open ball looks like. It totally depends on how the metric D is defined on the metric space. It may look like this way, or it may look like that, right? It depends. It totally depends on how the metric D is defined on that metric space. Yeah. Then, what is the good relation between those two definitions, the contact point and the convergence of a sequence in the metric space? That's what we want to, study in the next step. That's a lemma. That's a lemma. Okay, lemma. Again, we have a metric space X with its metric D. Then the first lemma is about what? The relation between the convergence on the metric space and the convergence on the real number line. Convergence of the sequence X of n to X on the metric space is equivalent to what? Equivalent to the convergence of the distance between X of n and X to 0 on the real number line. That's that's a very trivial relation between what? Yeah, if you look at the left-hand side over here, that's about the convergence on the D metric space. But if you look at the right-hand side, that's the convergence about what? Convergence on the real number line, because the distance between X of n and X, that's a real number. Okay? Yeah, so then, let me try to put this way, okay? Limit when n goes to infinity, distance between X of n and X converges to 0. That's what that means. Yeah, if you look at the left-hand side is about the convergence on the metric space X with its metric T. If you look at the right-hand side, that is the convergence on the real number line R with its metric, which is the absolute value thing, right? So that's a nice relation between the convergence on the metric space and the convergence on the real number line. Okay, that's pretty clear for you, and then I will leave its proof to you on the next homework assignment problem. That's easily proved. Just 1 or 2 lines, that will be enough to finish its proof. Then using this first lemma, we want to prove the second thing here, which is a nice relation between the contact point and the convergence of sequence on the metric space, general metric space. X naught is a contact point of the subset A, okay, subset A on the metric space X is equivalently the existence existence of a sequence converging to X naught. Existence of a sequence in A converging to converging to the point X naught. Okay, equivalently, there is a sequence X of n in the subset A converging to the contact point X naught. And those two statements are equivalent, and this statement tells us a nice relation between the contact point and the convergence of a sequence. You can easily, imagine, right? Geometrically. Then how did we write the closeness of the subset using what? Using convergence sequence. By the lemma down here. By the lemma, how did we write the closeness of a subset using the convergence of a sequence? Sequential convergence. By the lemma, the subset E is closed. Closed. If and only if, whenever x of n is a sequence in the subset E, okay, converging to x, the point x the sequence converges to must be what? Also in the subset E itself. Equivalently, okay? So, the closedness may be what? Re-expressed using what? The convergence of a sequence, like this, by the lemma over there, right? Yeah. We say that a subset E is closed if and only if the subset E contains all of its closed point. Then by the previous lemma here, okay, the subset E contains all of its closed point. Then what should it be equivalent to? No matter what sequence x of n in the subset E converging to x naught we choose, the point x must be what? Must be also what? In the subset E. Yeah? In the subset E. Because if you can choose a sequence x of n converging to x, then by the previous lemma, the point x, the sequence converging to x is what? If we can choose a sequence x of n converging to x, then by the lemma over here, the point x the sequence converges to is a contact point E already, right? Then, by the closeness here, the contact point E must be what? Also in the subset E itself for the closeness. So that's the equivalent sequential version for the closeness. And for example, how about the subset E in the second dimensional, two-dimensional Euclidean space? The subset E is the set of elements in the two-dimensional Euclidean space such that sum of squares of x and y coordinate is less than or equal to 1. You can easily draw its geometric picture on the two-dimensional Euclidean space. R2, two-dimensional Euclidean space with usual metric D we have used, right? That's exactly what? Closed unit ball around the origin in the R2 plane, right? The point, a collection of all x, y, all elements in the two-dimensional Euclidean space whose distance from 0 is less than or equal to 1, right? That's what that means. The closed ball. This is a closed set. Because this closed open ball contains all of its closed points, right? Actually, everything on this closed ball is a closed point of itself in this case. If you choose anything outside of that closed ball, and that's not a closed point, because we can easily what? We can easily take an open ball around it which does not contain any point in that closed ball at all, right? So, if you take any point outside of the closed ball, then those points are not contact point. But if you take any point inside the closed ball or on the boundary of the closed ball, and then that must be what? No matter what open ball around the point you choose, there must be what? Infinitely many points in that closed ball inside the open ball around. So actually everything on that closed ball is what? Is a contact point of itself. So this closed ball contains all of its closed points. So by the definition of the closeness, this closed ball is a closed set. But how about if you exclude 1 comma 0 from the closed open ball E? then that means that's everything in that closed ball around the 0 except 1 comma 0 down. So only 1 comma 0 is excluded from that closed ball. And then because of that exclusion, this excluded point is still a closed point of that closed ball, right? This set. But this, let's let that set be cap F. Then that cap F, this excluded point 1 comma 0 is a contact point of that F set, F is set, the subset F. But because that F does not contain this closed point, this contact point, we must say what? This subset capital F is not closed. Because this subset F excludes that contact point 1 comma 0. So that's not closed. Okay, that's not closed. Now I have another lemma here, which was what I have described here. We have a metric space X and let's let capital A be a subset of the whole metric space X, and then openness of the subset A is equivalently what? Its complement is closed. Its complement is closed. Which was what we have used as the definition of closeness on the real number line on the real analysis. But as I have already mentioned, we go a little backwards, okay, backwards, and then we use that as we develop, we justify this as the lemma here. Yeah. Then how do we prove this lemma here? How do we prove to go back forwards? Okay, we suppose the subset A is open, and then we prove its complement is closed. Its complement is closed. So suppose our subset A is open at the beginning, and we must show its complement is closed. To prove its complement is closed, we must show what? Its complement contains all of its cluster points, sorry, contact point in there. So let's let X naught, X naught, X naught, X naught be an arbitrary contact point of A complement. And then we prove that contact point X naught is what? In A complement as well, right? Yeah. Here is the whole metric space X, and we have an open set A on it. And then we must show its complement, which is outside of A, is closed. Now for that purpose, we take a contact point X naught of A complement, and we show that that contact point X naught is also what? In A complement. That's what we want to show. Then because X naught is an arbitrary contact point of A complement, it proves the closeness of A complement. Then let's use the definition of the contact point. And let's use the definition of the contact point. Because X naught is a contact point of A complement, there exists a sequence x of n in a complement such that the sequence x of n is converging to x naught. Yeah, there is a sequence x of n in a complement outside of A, converging to x naught. That's happened because x naught is a contact point of a complement. Then, how do we claim that that contact point x naught is still in a complement? That's what we want to claim. What happens otherwise? What happens otherwise? If not, otherwise, then that contact point x naught is what? In A. But since the subset A is open, right? Since the subset A is open, what must be happen? Okay, the contact point x naught is in A, which is open. Then what must be happen? Because the subset A is open and x naught is in A, by the definition of openness, there exists there is some positive number R such that the R neighborhood around the point x naught is still sitting in that open set A. Okay, x naught is in A, which is open. So by the definition of openness, there is some R neighborhood. There is some R neighborhood around x naught, which is still sitting in the open set A. That already tells you some contradiction, right? Because what the sequence x of n we have is must converge to that point x naught. But because this open neighborhood is in the subset A, but the sequence x of n is outside of A, but the sequence x of n must converge to that point x naught. That already a contradiction, right? But since the sequence x of n converges to x naught, the sequential points x of n must be in the R neighborhood around x naught for sufficiently large index numbers n. Now, more precisely, because x of n converges to x naught. Okay, for that R neighborhood around x naught, there must be some cutting line, okay, n over R, such that after that cutting line, the corresponding terms of the sequence x of n is sitting inside that R neighborhood around x naught. That's what I mean. But that's what it is about. That means what? Equivalently what? For sufficiently large index number n, the sequential terms x of n must be inside the R neighborhood around x naught. That's what it is about. So then what happens? The points x of n is in that open neighborhood, R neighborhood around the x naught. So each term, the sequential terms x of n must be in A, and also in where? Originally in a complement. That's a contradiction, which has never happened. That's a contradiction. Yeah, these sequential terms in that open neighborhood are sitting in A, but originally every sequential term x of n was what? In a complement originally. So that means what? Those sequential terms are in both A and A complement, which has never happened. So that's a contradiction. Why do you have that contradiction? We had that contradiction because we supposed the point x naught is in A complement. Sorry. We had that contradiction because we supposed the point x naught is in A. So we must conclude what? We must conclude there is no other choice. The point x naught must be in A complement definitely. So no matter what contact point x naught of the subset A complement we have chosen, the contact point x naught is still in A complement, which means A complement contains all of its contact point in there. Since x naught is arbitrary, contact point of A complement, then that means A complement contains all of its contact point in. A complement contains all of its contact point in, right? So that means what? A complement must be closed. There is no other choice. Okay, there is no other choice for that. So we did complete the proof of the forward direction. If a subset A is open, then its complement is closed. Now, how do you go backwards? We supposed A complement is closed, and then we prove A is open. The original set A is open then. Suppose A complement is closed. And we show that the original set A is open. For that purpose, let's let X be an arbitrary point in the subset A. Then we want to claim that what? We want to claim that there is some natural number n. There is some natural number n such that 1 over n neighborhood around the point X is still sitting in the subset A, and then that proves the openness of A, right? Yeah, X is an arbitrary point in the subset A. That's an arbitrary point in the subset A, and then we want to prove, we claim what? There is some 1 over n neighborhood around X, this open ball, which is still sitting inside A. Then that proves what? The openness of A. Then why is that claim true? What happens otherwise? Otherwise, what happens? If not, what happens? If not, what happens? We have to what? Describe the negation of this claim, right? Well, how do you write down the negation of that claim? No matter what natural number we choose, no matter what 1 over n neighborhood around X we choose, right? What? There is some point in the ball, but not in A, right? Which is not in A. If not, for all natural number n, there is some point x of n in the open ball, 1 over n neighborhood around X, such that the point x of n is not in A. That's what that means, right? That's exactly the negation of our claim. So if that claim is not true, and then no matter what n, 1 over n neighborhood around X we choose, there is some point x of n in that 1 over n neighborhood around X which is not sitting in A, right? That's what that is. That's exactly the negation of our claim. Then x of n is not in A, then equivalently what? X of n must be in A complement. In A complement. Yeah. Then do we see some contradiction already then? X of n is a sequence in the closed set A complement, converging to what? Converging to X, right? That's what it is. But where is X located? But X is in what? X is not in A complement. X is in A here, right? That's a contradiction to the closeness of A complement. Do you see that? You know, since X of n is in A complement, and the sequence X of n converges to X because each X of n is in the 1 over n neighborhood around X. The point X the sequence converges to must be in A complement because what? Since A complement is closed, assumed. So the point X is in A and A complement. The point X is in A, but point X must be also in what? A complement. That's a contradiction, which has never happened. Why is that contradiction happen? The contradiction is happened because we negated our claim. So we must accept that claim. That claim must be true. So no matter what point X in the subset A we choose, there is some 1 over n neighborhood around it which is still sitting in what? In the subset A. So we must conclude the subset A must be open. Okay? The subset A must be open, which was what we have desired. Okay, then let's continue next time. Okay? Let's continue next time. That's all for this week. I may, upload some new assignment problems on the Learning Hub. Okay? So please check it out.